In our last episode, we talked about where crime data comes from, who collects it, how it's classified, and what gets left out. Now we're going to take the next step, how that data turns into a prediction. Because predictive policing isn't magic, it's math. And that math follows a process, one that can be transparent and useful or opaque and dangerous, depending on how it's done. Most predictive models, whether they're used in finance, health, or policing, follow the same basic workflow. First, we want to define the question. What are we trying to predict? Second, we prepare the data. We want to clean it, structure it, and select the right variables. Third, we choose a model. Most commonly, we look to regression, a decision tree, or a machine learning algorithm. Fourth, we go through train and test process. Here we fit a model on past data, then see how well it predicts new cases. Finally, we validate and deploy. Here we evaluate performance, then apply it in the real world. The question shapes everything. If we ask, where will burglaries occur tomorrow? That's a place-based model. If we ask, who is most at risk of reoffending? That's a person-based model. And if we ask, when is crime most likely to surge? That's a temporal model. Each question creates a different target variable, a why in the modeling world. And getting that why right is harder than it sounds, because how you define the outcome determines what the algorithm will try to learn and what patterns it will ignore. Next comes feature engineering, the art of turning raw data into variables that represent meaningful patterns. In crime analytics, features might include number of crimes in the past 7, 30, or 90 days. We might have time of day and day of week. We might have distance to liquor stores, schools, or transit stops. We also can use population density, lighting, or income level. And finally, whether an area borders another high crime zone. Each feature is a hypothesis, a possible clue the model can test. Good features make a model insightful. Bad ones make it misleading. And sometimes a variable that seems neutral, like arrest count, secretly encodes bias because arrests reflect policing behavior, not necessarily crime itself. That's why transparency about inputs matters as much as accuracy of outputs. Once the data is ready, analysts choose a model, the mathematical framework that learns from the data and makes predictions. The most common starting point, logistic regression. It's interpretable, transparent, and predicts the probability of a binary event, crime or no crime. Each coefficient tells you how much a variable increases or decreases that likelihood. But when patterns get nonlinear or complex, analysts turn to machine learning methods like decision trees, which split data into if-then branches, random forests, which average many trees for stability, and gradient-boosted models, which learn patterns and stages for higher accuracy. These methods can capture subtle interactions, but they're also harder to interpret. You might know the prediction is accurate, but not why. And when algorithms start influencing real-world policing, why isn't optional. Building a model is only half the work. Testing it, that's where rigor comes in. Analysts split the data into training and testing sets, typically 70-30. They train the model on historical data, then see how well it predicts new, unseen data. Performance is measured with metrics like precision, recall, and AUC, which all capture different ways of being right or wrong. But accuracy isn't everything. A model that's 90% accurate might still systematically overpredict crime in certain neighborhoods. That's where fairness validation comes in, checking for patterns of bias by geography, race, or socioeconomic status. Once a model is trained, its predictions need to be visualized, and that's where maps come back in. For place-based models, results often appear as a heat map, red for high risk, blue for low. Each grid cell represents a predicted probability of crime within a given time window. For person-based models, output might look like a risk score or ranking list, who's most likely to be involved in future incidents. The key thing to remember, these are probabilities, not certainties. A 30% risk doesn't mean a crime will happen there. It means, statistically, it's more likely compared to others. But that nuance can easily get lost once numbers leave the analyst's desk. The final, but often forgotten, step in the pipeline is feedback. Once predictions inform patrol routes or policy decisions, new data comes back into the system. If police patrol an area more often, they record more incidents there, which confirms the model's prediction. And the cycle repeats. Without human oversight, the model doesn't just reflect bias, it amplifies it. That's why transparency, auditing, and continuous evaluation are so critical. Models don't create bias out of thin air, they automate whatever's already there. So that's how crime data becomes prediction, through a mix of statistics, software, and judgment calls. The technology is powerful, but it's also fragile, because behind every prediction is a chain of choices about what to measure, what to model, and what to trust. In our next episode, we'll look at hotspot science, why crime clusters the way it does, and whether mapping it actually helps reduce it.